All right, thanks so much. So I am really glad to be here. As noted, I am the Space Exploration Program Scientist within the NASA Space Weather Program, but I am brand new to headquarters as of last week. I'm not new to NASA, I'm coming from Marshall, but I am starting right out of the gate here. Fortunately, I have been involved with these programs for a number of years, but now I have the opportunity to approach them from a rather different perspective, and I'm excited about that. Heliophysics in general is eagerly working to catch up on integrating into the Artemis and the Moon to Mars exploration missions. And many of us are very keen to see this happen. So this talk will be at a very high level with the anticipation of a lot of potential for growth and depth as we move forward, which I'll speak to in a little bit. But the ultimate takeaway from this will be that there's a lot of heliophysics research that can and should be done from the moon. And in anticipation of traveling into deep space and also being at Mars in that deep space radiation environment, which is, of course, completely driven by the sun. So next slide. All right, so I want to spend a few minutes showing how the Space Weather Program in particular fits within the Moon to Mars architecture, starting here with this current vision, mission, and strategy, which we've been building from for a while now. This is organized in a very tractable and evolvable pathway. The yellow box is focused on what the division itself can do for research and science within our capabilities. So to observe the sun and the heliophysics phenomena, analyze and do that research and also modeling, which is a big part of our development strategy, and then work on predicting and improving the space weather forecasts and also nowcasting capabilities to be able to provide that information in real time to astronauts and also to those operating very critical infrastructure. The purple and green boxes are where we directly touch the space exploration programs. So transitioning those capabilities that we learn from and derive from those research programs into the operational environments, and then supporting those robotic and human exploration programs directly as well. And of course, we need to partner with many agencies, national, international, just to make sure that we are working towards consistent government directives. So all of these are also under work for updating. So that's why I have current being highlighted here. So some of these will be changed a little bit, such as number 5 may be added, we'll be adding support and leveraging the robotic and human exploration program. All right, next slide. Okay, so the high level goal for the space exploration or for space weather program and exploration is to address the high priority heliophysics science and space weather questions that are best accomplished using a combination of human explorers and robotic systems as we move further into deep space. And we have indeed been addressing this goal even before the first SLS launch. We've been using data for our space weather research from programs such as the MAVEN satellite, which is around Mars, and also the RAD instrument, which is on Curiosity on the ground, and that has been turned over to Heliophysics recently. And then we are already in preparation for Gateway. We do have an instrument that is going to be manifested on Gateway, and I'll speak to that in more detail in a little bit. Next slide, please. All right, and so there are currently 4 heliophysics specific science objectives in the Moon to Mars strategy, and Deborah showed these earlier, so I won't read through them. She did a great job describing these, and also the heliophysics use cases that are derived from these, so I won't go through them again. But I want to re-stress, as she pointed out, and as was pointed out right before I came on, that there's a lot of synergy between our heliophysics objectives with all of the other disciplines like lunar and planetary, human and biological sciences, and also physical sciences. And you'll see that a lot as I go through these slides. Next slide, please. And I just did want to point out that, again, those will also be undergoing some updates, especially as we start to trickle in the decadal report. All right, and for reference, I won't go through all of these, but these are also the science enabling objectives and the applied science objectives and the lunar infrastructure objectives that are directly tied into the Heliophysics Division and space weather. And these all trace from those higher level goals in that previous slide. And so these include science training for astronauts to perform high priority or transformational science on the surface of the moon. Also characterizing and monitoring the environments of the lunar and Martian surfaces, and also in orbit, which is really important to us as well for stuff for phenomena such as space weather and space weathering and dust, and also optimize the human-led science campaigns, specifically for heliophysics in our case. And then for the lunar infrastructure objective to monitor and derive the situational awareness and hopefully contribute to the early warning capabilities for astronauts, for crew, and for infrastructure. Next slide. Okay, so here I want to touch on the heliophysics science and research that benefits from going to the moon and having the moon be accessible, including, but also beyond just the dynamic radiation environment. So there have been a few studies that have been performed addressing this subject. In particular, this report, which came out in 2007, which is similar to the astrobiology one, that was presented just a few minutes ago. And this was from the National Advisory Council with the Heliophysics Subcommittee. And so a lot of this report is still completely relevant, but we are at an important crossroads for updating what we want and what we can do now. So I asked those with heliophysics specific ideas to review this document to see what needs to be updated and or stressed. So next slide. Okay, and so the following set of slides here will provide some example concepts that I've pulled from the contributed white papers to our current decadal that hasn't come out yet. Hopefully it'll come out in the fall. So, and this was just because I wanted to highlight some of the stuff that the community has expressed interest in very recently, including myself. I was in there as well. So you can find all of these white papers here in this bulletin, and you will likely notice that there is a lot of overlap with all of the disciplines that have already presented here for their science. And I did want to put this disclaimer that I'm simply highlighting these. I am not in any way endorsing these because we don't know what's going to come out of the decadal yet. All right, next slide. Okay. So this one is really a catch-all for all of the fundamental physics research that can be done from the moon, because the moon is such a unique heliophysics laboratory, which is soon hopefully to be accessible in ways that have never been done before, such as kinetic plasma physics, including wave particle interactions, because the moon is a source of charged particles, but it is also a source of plasma wave disturbances. Small scale magnetic fields, because they interact with the solar wind, they impact the plasma flow, they reflect the solar wind, they create shocks and possibly undergo reconnection. All of this is relevant research, not only for space weather, but for plasma physics and solar physics in general. There's also in situ measurements are really important in cislunar space and also on the lunar surface. Radiation sensors for plasma and field measurements are really important for heliophysics research. Understanding the potentials and the currents near the surface that potentially affect sensitive instrumentation, along with dusty plasma. Not only is that an important source of research, but it's also highly effective on instrumentation or impactful on instrumentation. So that's another important science topic. And then also remote geospace observations are an important factor here, because we have this potential for an excellent low noise resource that's a rich platform that we could look back at the Earth to observe the breathing of the magnetosphere, for example, in response to space weather events, and also looking out at the solar system's heliosheath as an example. Next slide, please. And collecting rocks is not just for geologists. Lunar samples can also help solar physicists trace the evolution of the sun because it's a nice chronologically preserved capsule of solar activity, and also the impacts on other planetary bodies within the solar system. And that information will help us to constrain models of future evolution of the sun as well. So the time is now to begin supplying inputs on the types of samples that we would need, as well as the protocols for handling those samples. Next slide, please. And of course, there's space weathering, which has been mentioned a couple of times now already, so I won't go into too much detail here, but it's important to understand the effects of space weathering on the surface because that tells us a lot about the processes that are involved, and it's also applicable to other airless bodies in the solar system. Example measurements here would be SEPs, which are solar energetic particles, and their associated vents, and how they interact with the local plasma and how that's variable. And then looking for signatures of localized impacts on samples relative to the ambient plasma environment. And then also looking at the solar plasma interactions at the lunar poles, in particular with impacts on the frozen volatiles. Next slide, please. Okay, so of course we want to maximize our integration with the Artemis program so that we can make these huge leaps in science and exploration. But it requires being involved all along the way so that the folks who are doing so much work and so much effort on the mission planning and the requirement allocations and so forth are not completely caught off guard and can hopefully accommodate some of the things that we need. Otherwise, there will be gaps in what we can provide and what we can do. And you could tell from the morning session that there are so many moving parts involved with this train. So the time is now. One example for heliophysics in particular are the needs for high-speed communications relays, and that's really important if we're getting solar data and we need to analyze that on the spot and communicate that to astronauts or to people on the ground who are maintaining the infrastructure. Also, for research, we would need pointing platforms for remote sensing instruments, for example. And we could also make use of the logistics modules because those are basically thrown away after they're being used. And if we could put them in specific orbits around the sun, then we could get more of a 3D view of the sun. So those sorts of ideas are really important to be able to communicate early rather than later when it's not possible. All right, next slide. Okay, so while this is a surface science workshop, it's also really important to recognize that cislunar in space is also really important to heliophysics because it offers a really unique perspective of the moon, the sun, and geospace. For instance, we can use the moon itself as an occulter for coronal studies. It's a really good, clean edge rather than some of our instrumentation where we don't get quite as clean of an edge. And this is only right now obtainable through short duration sporadic eclipses. But if we could use the moon, we have more access to it. It's also a favorable vantage point for accessing in situ solar wind. So we get this in the protected environment within the magnetosphere, but also in the deep space environment. So this gives us a lot of variability and more information about what the difference is between the two environments. All right, next slide. And as I said, there's Hermes, which will be NASA's first science payload on Gateway. It'll be launched externally on the Halo, already manifested. And it will have a suite of instruments for measuring particles and fields, and that will analyze the solar wind environment in and out of the magnetosphere. So we're really excited about this one, and it will serve as a pathfinder for mission enabling and mission enhancing space weather payloads in the future. And there will be complementary payloads as well on the manifest from ESA and from ESA and JAXA, named Ursa and Ida. All right, next slide. So looking ahead, next slide, please. There are a lot of updates and work, especially in the Space Weather Program in the Heliophysics Division. The director there is Jamie Favors and is coordinating all of this. But this is definitely key timing for community inputs. So right now we are updating that vision, strategy, and implementation plan, as already mentioned. Key input will be the decadal. We don't have that yet. We're expecting that sometime this fall. And we're hoping to put together a heliophysics specific workshop for the community to gather all of these inputs so that we can incorporate them into this vision and strategy and implementation plan. So we'll be talking about science questions that can be done on the moon, around the moon, and at Mars, operational support needs, and also thinking forward to space weather payloads. And we're hoping to also have future research solicitations through the Space Weather Program. So, and I'll be facilitating one of the breakout sessions, and I'm hoping to bring back some good ideas from you all. Thank you.